So this spreadsheet is designed to help you calculate the pressure losses in your pipe system when you design it coming out of your pump. And the way it's set up at the moment is it's designed or set up at the moment to calculate the pressure losses in this fictitious pipe system here. So in this pipe system here, what we have, we've got three straight sections that we call S1, S2, and S3, in which there will be major losses between the fluid and the inner wall of the pipe due to friction. And there will be minor losses at the 180-degree bend, the converging nozzle, and the inlet and the outlet, which are fittings of sorts. So over here we see the pipe characteristic curve. And if I click on it, you'll see that it's drawing the data from this system curve here and plotting it against these volumetric flow rates over here. And if I click on one of the cells here, you'll see that it's summing up these major loss values here and these minor loss values here in red as well. So you've got S1, S2, and S3. You've got the entry, the exit, the 180-degree bend, and the reducing nozzle, all being added to produce this value. And then that's done over a range of flow rates to produce this pipe characteristic curve. So how do we arrive at these values here? The starting point, if we want to calculate the major losses in S1, S2, and S3, is to calculate Reynolds number first of all. So that's done in this section. And then that feeds in to this section here, these three columns here, to calculate the friction factor in S1, S2, and S3. And then they feed in to calculating the major loss for S1, 2, and 3 in these three columns here. So we'll start with the Reynolds number. Reynolds number, we have S1, S2, and S3. We have the diameters, we have the lengths of those sections, and we have the relative roughness, which is the surface roughness on the inside of the pipe divided by the inner diameter of the pipe. And then we have Reynolds number typed in here. You'll see the equation written up here. But one thing to note about it is it's in this form where it's got the velocity for the diameter divided by the kinematic viscosity. But rather than it being expressed in terms of the velocity, it's being expressed in terms of the volumetric flow rate. So it can pull from this cell over here. So that's why it'll look different when you see the equation actually typed in there, because the volumetric flow rate equals the velocity by the area. So just to keep that in mind. The Reynolds number feeds into calculating the friction factor then in the corresponding cell for S1, 2, and 3. The friction factor is based on the Moody diagram, or usually obtained from the Moody diagram. But the Moody diagram is based on this complex state equation down here. And so that is typed into this cell for you to calculate the friction factor based on Reynolds number. And then the friction factor feeds in to calculating the major loss. So you'll see the major loss equation up here, and it requires the friction factor. But this is also normally expressed in terms of the velocity V. But we want to express it in terms of the volumetric flow rate, so it can refer to this cell over here. So when you arrange it, Q being V by A, once again, you'll see it expressed in the cell like this, multiplied by Q. So that's how we get the major loss in terms of the volumetric flow rate. So that's the major losses in S1, S2, and S3, and then done over the range of flow rates. Then we have minor losses at the entry, the exit, the 180-degree bend, and the reducing nozzle. This is the minor loss equation up here, and the K factor, excuse me, is outlined at the top. Once again, it's normally expressed in terms of the volumetric flow rate, but normally expressed in terms of the velocity of the fluid, but we're going to express it in that equation form in terms of the volumetric flow rate Q here, so we can pull from this column. So when you click on it, it looks like this. And if you were to examine that, you'll see that it's in this form here. Okay, so all these values here add up to produce this cell value over here. And that ultimately produces our system curve. So what's going on with the other curves? Well, let's say we add a nozzle on the end of the pipe over here. What the nozzle does is it reduces the diameter, the outlet diameter, and as a consequence, increases the velocity. So as you add in a nozzle, if I click on system curve here, it's pulling this data and plotting it against the volumetric flow rates. And if I click on one of these cells, you'll see that it's a combination of the major and minor losses plus a nozzle that has a K factor of 4. And then if we were to click on the next system curve, you'll see system curve 3. And if I click on this, it's actually adding up all the major and minor losses and a nozzle with a K factor of 8 and so on. So the idea there is if you add a nozzle at the end of your pipe, you will decrease the area, increase the velocity coming out, but it will have an effect on the flow rate and also increase the pressure losses from the pipe. So that there's a trade-off. You can find the optimum point where you're increasing the velocity, but not significantly affecting the pressure loss too much. Okay, so basically what you have to do is, you've got a blank version of this down here. You can try and fill it in yourself to produce those system curves. That's on the other sheet, to see if you can understand it. And then what you need to do is you need to delete these values here and the pump curve values here and bring in the values from the other Excel sheet up on Loop, the pump characteristic curve values, and put those flow rates and those pump head values in here. And then you adopt these columns. So for example, you might have 5 straight sections, so you'll add 2 columns in there. You might only have 2, so you'll have to delete 1, for example. You'll put in your diameters, your lengths, and your relative roughness, which will be this value divided by the inner diameter of your nylon tubing. These values will update, and these values will update, and these values will update. You will have to decide on your minor losses. So you'll have an entry with a K value of 0.5. You'll have an exit with a K value of 1. You will have a 90-degree bend as opposed to a 180-degree bend outlined here. And you'll have a K factor of 0.75 for that. The nozzle you'll have to design yourself and produce a K factor. I'll go through that next week with you. And then you will produce your system curve. So that's it. So have a go filling in the rest of this sheet to see if you can understand it. And then when you've designed your outlet pipe, you can either add in or delete columns over here, and you'll update the information, flow rates, pump pressure values, and your diameters and lengths and so on. Okay.